In the previous video, we talked about the sequence of the function. Okay, so we're gonna continue doing the sequence of the function by I'm gonna discuss about the picture of the sequence. When we have the sequence, how could we imagine what it's gonna be like? So the thing that you see in the sequence picture here is going to be you have an equal to 5. It means that you have n equal to 1, n equal to 2, equal to 3. You're going to have the value of an turn out to be 5. And this one is just going to be constant sequence. So this one, I'm going to say that this guy is a constant sequence. Okay, so you have this one is a constant sequence and you have, it's gonna turn out to give you the graph. So you see that the graph turned out to be a point on constant line y equal to 5. So this one is gonna be the graph between n and an. Okay, so it's going to be graph between n and an, and you see that the graph is not going to be continuous. It's going to be just point that on a constant line. The next one is going to be n over n plus 1 that we had before. So the sequence n over n plus 1, you see that if you plot the graph, it's going to turn out to be 1/2 here, and it's going to be 2/3, 3/4, and so on. And you see that the graph turned out to be the point that is going to be lies on the curve y equal to x over x plus 1. Okay, so this one is curve y equal to x over x plus 1, and the graph is continue. So it's going to be this point, this point, this point. It's not going to be continuous like we had last semester. It's going to be just point, and when you plug in n equal to 2, n equal to 20, n equal to 30, it's going to be continue growing. The next one is the graph of an equal to arctan n. Okay, so you see it's going to be shape of the graph of arctan when n equal to 1. Okay, so arctan 1 is pi over 4, and pi over 4 is about 3.14 over 4, and you're gonna get the number. Okay, so it's going to be arctan 1, arctan 2, arctan 3, until arctan 25, and until arctan infinity. The next one is going to be 2n minus 1. Okay, so it's going to be an increasing line, 2n minus 1, that has a slope equal to 2. Okay, and you have graph 2 to the n and 0.5 to the n. And you have also the graph of negative 1 to the n. Okay, so for this one, you see that it's gonna turn out to give you the shape of the graph like this one. And it's gonna be, when you imagine the sequence, it's gonna be just point. Okay, so it's not gonna be continuous curve like we have in calculus 1. The next thing that we're gonna study is gonna be about convergence or divergence. So the thing that the topic say here is going to be about convergence and divergence. The convergence and divergence sequence is mean that we are finding the limit of the sequence. And the limit that we gonna find is going to be the limit n go to infinity. Because you see that the picture here is not possible to talk about the limit at the point, because the function turned out to be not continuous, and we not be able to see that it's going to be approached to a point or something. So it's not happen that way. So the thing that we shall discuss is going to be, we're going to discuss about limit n go to infinity. Okay, so for convergent, divergent here, it's going to be about limit n go to infinity of an. Okay, so it's going to be, we are computing this one. So it means that we like to know the behavior when n go to infinity of the sequence. So we want the behavior of the sequence when n is large Okay, so we want the behavior of the value of an when n is large. So this is the thing that we gonna do for infinite sequences. Okay, so this is gonna be, so this one will be the thing that we would gonna spend time studying. Okay, so we gonna spend time studying this guy limit n go to infinity of an. Okay, so let's see the picture first. So you see here that if you increase n, okay, let's do the first example. If you increase n, this guy gonna continue going to 5. Okay, so this guy gonna continue going to 5. Okay, so in this case, we're gonna say that limit n go to infinity of 5 turn out to be just 5. Like we had in calculus 1, but the variable that we are using turned out to be n instead of x. Okay, so it's going to be the technique and everything that we have studied in calculus 1 will be used here for finding the limit n go to infinity. The notation will be kind of the same except we use n instead of x. The next one is going to be y equal to n over n plus 1. And you see that this sequence will be approaching. Okay, so you see that if you look at the line 1 here, okay, so if you look at the line y equal to 1 here, you're gonna see that this y equal to x over x plus 1 when x go to infinity, this guy will be approaching this line. Okay, so when n go to infinity, it's gonna kind of close to this line. It's gonna be like the concept of the limit that we have seen last semester. So in this case, we're gonna write limit n go to infinity of n over n plus 1 turn out to be equal to 1, okay, by computing the limit like this one. Okay, so that come from the picture. The next one for an equal to arctan n, we use cal 1, okay. Cal 1 we learned that limit x go to infinity of arctan x, this guy is going to be pi over 2. So when we have calculus 2, so we're going to just have the same thing, except instead we're going to use the variable n. Okay, so it's going to be limit n go to infinity of arctan n turn out to be pi over 2. The next one, you see an equal to 2n minus 1, and you have n go to infinity. So you see this guy gonna be increasing with an upper bound. So you see that you have limit n go to infinity of 2n minus 1 turn out to be infinity. Okay, so it's going to be limit n go to infinity of 2n minus 1 turn out to be infinity. And for these two guys, so you have 2 to the n and 0.5 to the n. So you see for y equal to 2 to the n, is this picture is going to be increasing graph, and you have y equal to 0.5 to the n. This guy is just 1/2 to the n. So it's going to turn out to be decreasing graph. And we see that limit n go to infinity of 2 to the n turn out to be infinity. And you have limit n go to infinity of 0.5 to the n. It's going to tend to see, you see that it's going to become lower, 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 and it's going to be approaching 0. Okay, so that will be this guy. Okay, and you're gonna have limit n go to infinity of -1 to the n. So for this one, you see that this one is going to be alternate up and down. When n equal to 1, it's going to be -1. Okay, so n equal to 1, n equal to 3, n equal to 5. Okay, so it's going to turn out to be n odd. It's going to turn out to be -1. And you have n equal to 2, n equal to 4, n equal to 6. Okay, and in this case, n is even. It's going to be +1, so it's going to be 1. So you see that this one is called, so the sequence -1 to the n is an alternating sequence. Okay, and you see that it's going to be up, down, up, down, up, down, and you're not going to have, and okay, it does not approach a unique limit. Hence, in this case, it's going to turn out to be no limit. Okay, so we're going to conclude that it has no limit. So, it has no limit. Okay, so you're gonna conclude that this guy will have no limit, or the limit does not exist like that semester. So the thing that we are doing so far turned out to be we gonna just see the limit of the sequence by looking at the picture. Okay, so for this one, you see that it's gonna be limit n go to infinity of arctan n over n plus 1. Okay, so when we have limit n go to infinity of arctan n over n plus 1, and you see that if you consider the limit of the pink guy only, it's gonna turn out to be equal to 1. Okay, so if you consider the limit of the pink guy, so this guy is equal to 1. Okay, so this one will have the limit equal to arctan 1, and arctan 1 equal to pi over 4. Okay, so this limit turned out to be equal to pi over 4. Okay, and pi over 4, you see that it's gonna be somewhere here. Okay, so that you can see. So it's gonna be like this. Okay, so it's gonna be the line pi over 4, which is about 0.7, almost 0.8. Okay, one last thing, you see that this one discussing about limit n go to infinity of log n. Okay, limit n go to infinity of log n. If you study last semester, it's going to be log infinity, and log infinity is infinity. So it's turned out to be no limit. Okay, so limit does not exist. Okay, so far we learned how to find the limit by the techniques called using the picture or using the graph of the sequence. And the graph of the sequence turned out to be the point when n equal to 1, n equal to 2, n equal to a positive integer. Okay. The next thing that I will teach you is going to be the way that we're going to find the limit by using the limit theorem. Before I do that, let's talk about the definition of conversion and divergence a little bit. So we're gonna say that the sequence is conversion, or the sequence convert to the limit L if you have eventually the term of the sequence are closer and closer to L. So this one is gonna be conversion with the limit equal to L, okay? And you're gonna have the divergence. Okay, so the conversion here is mean that you have limit n go to infinity of an equal to a unique limit L, and you're gonna have a diversion if the sequence an has no limit, does not have limit. Okay, so it's gonna be the name for conversion or diversion. Okay, so it's gonna be conversion in the first case, diversion for the rest of the case. So for example, n equal to 1 over n, when n go to infinity, this one is gonna be 1 over infinity, and it will approach 0. When you have an equal to 1 plus 0.5 to the n, it's going to be this guy gonna approach 0. So it's going to be 1, okay? And you have an equal to arctan n, so it's going to be pi over 2, like we did in the picture before. Okay, and in the conversion case, it's going to be an is conversion. Okay, so it's going to be an is conversion. The next one is about diversion. About the diversion is mean that you have no limit or the limit not approach to a unique point. For example, you have n go to infinity of n, so it's going to turn out to be infinity. This one is going to be 1 or minus 1. So it's going to be has no unique limit. Okay, does not approach, does not approach a unique limit. Okay, and you have 3 to the n, this guy gonna go to infinity. And we can have the value of r, that r to the n is conversion. Okay, so this one, when r positive, not equal to 1, this one will be exponential. Okay, and you're gonna have, when r negative, it's gonna be alternating sequence. And the sequence is gonna be conversion. Okay, so it's gonna be r to the n here. It's gonna turn out to be convert to 0 if absolute value of r is smaller than 1. Okay, it's gonna turn out to be 0 if r equal to 0. Sorry, it's gonna be equal to 1 if r equal to 1. It's gonna be, if you have r equal to negative 1, it's gonna be diversion. Okay, so it's gonna be negative 1 to the n. Okay, so it's gonna be diversion. And if you have absolute r more than 1, it's gonna turn out to be diversion. Okay, so it's gonna turn out to be something like a negative 2 to the n, negative pi to the n like this. This one will have the graph that you are unable to control. Okay, so let me just give you a small graph here. So it's going to be the graph that is going to be alternate and you not be able to control the shape. So it's going to be here and it's going to be somewhere large here and it's going to be larger and larger and it's become larger. So you see that it's going to become alternate and it's going to become larger and larger without any upper bound. So you not be able to control it in the case that you have the absolute value of r greater than 1 and for r equal to r more than 1. So let's try 3 to the n, 3 to the n. So for 3 to the n, this one is going to be look like this picture. Okay, so it's going to be look like this picture. So it's going to be increasing without an upper bound. So it's going to fall into this case as well. Okay, so let's memorize. So when you have the thing that you need to memorize will be two cases. The pink one, okay, so the pink one, when you have absolute R is more than 1, it's going to turn out to be divergent. And the blue one, when you have absolute R less than 1, it's going to turn out to be convergent. And let me also give you several examples here. If I ask you, okay, to the end, okay, if I ask you 1.05, not 1.05, negative 1.05 to the end, okay, and you have negative 0.08 to the end, okay, something like this, and you have e to the end, okay. So you see that for 2 to the n, you have r equal to 2 more than 1. Okay, so it's divergent. If you have, in this case, r equal to negative 1.05, okay, r equal to negative 1.05, so you have absolute r more than 1, so it is also divergent. And you have r equal to negative 0.08. So you would get absolute r less than 1. So in this case, it is convergent. And here you have r equal to e, and e is about 2.718. So more than 1. So it would be divergent. But if I have e to the negative n, okay, if I have e to the negative n, this sequence turns out to be 1 over e to the n, and you have r equal to 1 over e, and 1 over e is smaller than 1, okay, so it's going to be 1 over 2. 0.718 is smaller than 1, so it would give you conversion. Okay, so it's going to be convergent and divergent, and it's going to turn out to be the number r that you use in order to determine conversion or diversion. Okay, so you are looking only inside parentheses like this one. Okay, so that will be the thing that you use to determine the conversion, diversion of this kind of sequence. Okay, and this sequence in this form is called, so have a name for this one, is called geometric sequence. Okay, so this guy is called geometric sequence. Okay, so it's going to be some name that you may have to recognize. Okay, so let me conclude. Okay, so let me conclude that if you have t positive, okay, you like to find limit n go to infinity of 1 over n to the t. So this guy will be equal to 0. So this guy is going to become 0. And if you have limit n go to infinity of n to the t, it's going to be infinity. For example, if you compute limit n go to infinity of 1 over root n, so this guy is going to be 0. If you have limit n go to infinity of n to the fifth, it's going to become infinity. And number 2, you see that it's going to be discussing about limit n go to infinity of r to the n. It's going to turn out to be 0 when you have the blue case. Okay, so that is the blue case that we have up there. Okay, so the blue case. And for the pink one, it's gonna turn out to be, when you have more than one, it's gonna turn out to be going up without an upper bound, so it's gonna be infinity. However, if you have less than or equal to -1, it's gonna turn out to be does not exist. Okay, so that will be just for number 2 for the pink case. And you still have the basic property of the limit that allows you to it's going to be, you have limit n go to infinity of constant, it's going to become constant, limit n go to infinity of kan, you allow to move k to the front and you just find the limit n go to infinity of an. Okay, so for this one, it's going to be 2 formula. Let me put some comma here. And you have the sum or the difference of the limit and the product of the limit that you can use calculus one in order to find the limit. And you also have the technique called using the squeeze theorem. The squeeze theorem, you see that, okay, so for this one, okay, I think, okay, for this one, you have the limit in the middle, lie between an and cn, okay, and you have the limit of an and limit of cn turn out to be equal to L. This one you'll be able to conclude by squeeze theorem or by sandwich theorem that you're gonna have the limit of the middle guy equal to L as well. So this one will be the one that we had before in calculus one as well. I'm gonna review this one later. And you will also be able to use L'Hopital in order to compute the limit, okay? Let's do several examples, okay, before I finish this clip. So I'm gonna finish 1, 2, 3, okay, and I'm gonna leave you some example for you on your own. So for this one, you have n over 2n minus 1. The way to compute this limit turn out to be, you like to compute limit n go to infinity of n over 2n minus 1. This one, you just have n and you pull out n, so it's going to be 2 minus 1 over n, and you get rid of this n. Okay, so this one will become 1 over 2 minus 1 over n. And when you have n go to infinity, this guy becomes 0. Okay, so when you have n go to infinity, this guy becomes 0. And so the limit turned out to be n over 2n minus 1 turned out to be 1/2. Okay, so that limit turned out to be equal to 1/2. The second one, you see, let me also mention that you can use L'Hopital, okay, or you can use L'Hopital. So you see that this one will be limit n go to infinity of n over 2n minus 1. And if you like to use L'Hopital, you're gonna differentiate on top, on the bottom. So this one is L'Hopital in terms of infinite over infinite. So you see that it's going to be limit n go to infinity, and you differentiate on top, you get 1, differentiate on the bottom, you get 2. Okay, so you dip the top guy, dip the bottom guy, and you see that it will become limit equal to 1/2 also. Okay, so you can use just the basic simplification, or you can just use the L'Hopital in order to find this limit. The third one, the second one, you see that this one is too complicated for using L'Hopital. Okay, so I'm gonna mention first that this guy is a little bit too complicated to differentiate. Okay, so this one is a little bit complicated to differentiate. So we're gonna try to simplify. So the way to simplify this one is gonna be you have limit n go to infinity, and you see that it's gonna be n, and it's gonna be the third root of n cubed plus 4, and it's gonna be 16 n squared minus 5. Okay, and you see that on top you're gonna pull out n. Okay, and you're gonna see that inside square root is gonna be n cubed 1 plus 4 over n cubed. Okay, and on the bottom it's gonna be 16, so it's gonna be n squared, and you have 16 minus 5 over n squared. Okay, and here you see that this one will be limit n go to infinity, and you have n plus the third root of n cubed, the third root of 1 over 4 over n cubed. Okay, and here you get n square, square root, and 16 minus 5 over n square. And you see that this guy turned out to be equal to just n. So you're gonna have this term and this term out. So it's gonna be n, and it's gonna be 1 plus square root 1 plus 4 over n cubed. Okay, and you have also this term, okay, to be n. Okay, so this one will be n. Okay, and you have square root 16 5 over n squared. Okay, and you see that this guy and this guy get rid of each other nicely, and you see that you're gonna just take the limit n go to infinity. So this term becomes 0, and this term also becomes 0. So this would allow us to have, okay, so it's going to be 1 plus root 1 over root 16. So it's going to be 2 over 4 equal to 1/4. Okay, so you have the second question. Okay, so you see that it's not that easy to do. Okay, so for number 3, you see that it seems complicated because we are talking about the log function. However, this one turned out to be able to simplify into log 2 over n plus 1. Okay, so it's going to be this one, and you allow to compute the limit n go to infinity of log 2 over n plus 1 by just computing the limit of the pink guy. Okay, so you compute the limit of the pink guy first and then you plug in. Okay, so we consider the limit n go to infinity of 2n over n plus 1, and this one you see that you can use L'Hopital a little bit, so it's going to be 2 over 1, so it would be just 2. So the limit of the pink guy turned out to be 2, so this one will be just log of 2. Okay, and that will be just easy. Okay, so for this one, it's going to be you just compute the limit behind the log and then you plug into the function. You see whether you get the finite limit. Okay, for number 4, I will let you do this one by yourself first. So I'm gonna recommend that you compute the limit of the exponential. So it's gonna be that you compute the blue limit of the exponent first, and then the thing gonna have the limit equal to e to that limit. Okay, so it's not that hard to do. The number 5, okay, for number 5, you see that it's going to be square root n square minus n plus 5 minus n. Okay, so for this one, in order to compute this limit, we need to simplify. Okay, so it's going to be limit n go to infinity, square root n square minus n plus 5 minus n. It's going to be limit n go to infinity. The way to simplify is going to be like last semester. So it's going to be you're going to multiply the top and the bottom by the opposite side. So it's going to be n squared minus n plus 5 plus n square root n squared minus n plus 5 plus n. Okay. And you see that you can multiply this guy and this guy together to get, okay, so to get the different square, and this one will become limit n go to infinity of n square minus n plus 5 minus n square, and you have the green one. Okay, so you have the green one, and you're gonna simplify the top one to be negative n plus 5, the bottom one to be the green one. Okay, and you're gonna follow number 2 to complete this question. Okay, so use number 2. Okay, so I will let you do this one on your own a little bit. So it's going to be similar to the one that we did in number 2. I'm going to give you the solution during the recitation for this one. Okay. Okay, so let's do the last one. The last one, you have 3 to the n plus e to the n over pi to the n minus 2. So you see that in comparison, you have 3 more than e and 3 less than pi. Okay, so you compare these 3 numbers, e, 3, and pi. So you see that the highest one is pi and the lowest one is e. So when you do this one, you're gonna think about limit n go to infinity of r to the n is 0 when you have absolute value of r is smaller than 1. So when we think about this property of the limit of r to the n that you see here, you're gonna make the denominator to be, and try to make, okay, try to make the base smaller than 1. Okay, so we're gonna try to make the base smaller than 1. So you see the term here is 3 to the n e to the n over pi to the n plus minus 2. So you see that if you divide the top by pi to the n and the bottom by pi to the n, you're gonna obtain, okay, so you're gonna obtain 3 over pi to the n e over pi to the n and 1 minus 2 over pi to the n. Okay, so you see we have divide the whole thing by pi. Why did I do that? Because I know that pi is the largest, so I divide the whole thing by pi. Okay, so this guy become e over pi, 3 over pi. This guy become less than 1. Okay, so this guy become less than 1. So in this case, you see that this r, okay, so this r turn out to be smaller than 1, and you see that this one turned out to be 2. Okay, let me write in this way, so it's going to be 2, 1 over pi to the n, and this one turned out to become less than 1. And you have this limit turn out to be 0, 0, 0. Okay, so you see that you have the limit turn out to become 0. So let this class limit n go to infinity. Okay, so it's going to be, so in this case, okay, so in this case, it's gonna turn out to be, okay, so in this case, it's gonna turn out to be 0 plus 0 over 1 minus 0. And it will become 0. Okay, and this one will be just the limit that you have. Okay, so let's try one more example by yourself. So if I give you negative 2 to the n plus 4 to the n over 5, 3 times 5 to the n plus 2. Let's do this one on your own. Okay, so for this sequence, okay, try this one and I will give you the solution during the recitation. Okay, so this one is 3 times. Let me make this guy a little bit clearer. Okay, and that will be the thing is that you have. Okay, so that would be all of the thing that for the lecture of the first sequence, we're gonna have the follow-up about the limit that is gonna be more technical, like you are using L'Hopital and you're gonna use the thing that called squeeze theorem in order to solve this limit of the sequence in the next clip. Okay, so it's gonna be long topic. Okay, so this one is gonna be just the simple one first. Okay, so that's it.